I would like to thank the organizers for giving me the opportunity to give this talk. So what do I want to talk about? What do I mean by p-adic varieties? So this will be algebraic varieties or analytic varieties over local fields of this characteristic or something similar to that. And now the Rham cohomology of such varieties naturally comes with equipped with the Hodge filtration, but there are also structures which we call hidden structures, which are more of arithmetic origin. They come from the existence of reduction mod P, and those are Frobenius monodromy. And there is a non-trivial relationship between filtrations and the Frobenius and the monodromy. And this is what I want to talk about. That is what kind of interaction we see. What do we know? So in the algebraic case, the story is pretty well understood. And it's now like, I don't know, 40 years maybe that we are working on that. In the analytic case, it's just starting the story. It's like 10 years maybe. We don't know that much. So I will tell you what we know. Okay, so the setup will be the following. We will have x prime, and then K is going to be complete this evaluation field, mixed characteristic 0p, and we will have ring of integers for the notation and the residue field. You can think for simplicity, if you like, about as finite extensions of QP. And what else do I need? So C is going to be the completion of an algebraic closure of K bar, which is also algebraically closed now. And the Galois group, which will appear all over the story, is going to be the Galois group of K bar over K. And that's all I need. For the notation, so let's look at the first case, which is the case of algebraic varieties. So they are going to be over K. So I'm simplifying the story. There is an analogous story which starts with C data, which in algebraic case maybe is not so important because you can descend, but in analytic case, the fact that you are working over this C, not over K, actually makes a difference. Okay, and let's start with a simplest case, smooth and proper variety first. So we are looking at two naturally attached cohomology groups to that, and one is the Rham cohomology, or the whole Rham complex. And I will just skip if it's understood. And this is defined using algebraic differential forms. Number one, which is of interest to arithmeticians, is the geometric étale cohomology, and I'm going to take the one with p-adic coefficients because that's the one which is related to this Rham cohomology.
What's the subscript? The
C is this C. Like CP. So here, by transfer of structure, you have an action of the Galois group, and now by comparison theorems and standard comparison theorems in étale cohomology and period isomorphism, you know that they have the same finite rank over QP over K and QP respectively. So as groups, as vector spaces over K and over QP, they compare. Okay. This was a very basic start. And now let's look at the first structure I wanted to talk about, which was the Hodge filtration. So if I look at the Rham complex, which I will write this way, so this is defined as coherent cohomology or cohomology of the complex of differential forms of X over K. And these again are algebraic in our case. And now that we are Hodge filtration, we can define as the cohomology of the truncation at R under the simple truncation of this Rham complex. Now there is also naive filtration, which we often in this context, algebraic context, talk about, which is defined as filtration on the cohomology group, the Rham cohomology group, which is going to be defined as the image of so this should be shifted, of course. So HI of so this is naive filtration. Okay, so what do we know about this filtration and associated gradings? So let me look at some conjectures which are now theorems. We start with Tate. So that's around 67. I think if I got the date right. So he formulated the following conjecture, which we now call Hodge-Tate comparison conjecture. So it says the following: you look at this as cohomology with 3 coefficients, but you look at it as a Galois representation. And now what Tate was suggesting is that if you extend the coefficients, so these are finite rank vector spaces, if you extend the coefficients to see that this representation trivializes in the following sense. So it trivializes with multiplicities which come from the Hodge data. So it splits into a direct sum of Hodge cohomologies and here the twist refers to the twisting by cyclotomic character. Power minus I. So this is very nice, right? So basically, when you extend your coefficients to this period ring, C, then all you see is cyclotomic characters, and the multiplicities come from the Hodge data.
What is the period ring? The C?
So this is just an example of a period ring.
But it's not a field. So
it's a field.
It's also you call it period ring.
This is the simplest. You will see others.
Which are not fields.
Which are not fields. Not always fields. Yeah, but that one is a field, yes. And then he proved it. So Tate proved it. Proved it for abelian varieties, where this has particularly simple form, right? So we are saying that we just care about H1 of an abelian variety extended to C, split into H1 and then we have squeezed by minus. So this should be extended to C. Squeezed by minus 1, sorry. Minus 1. And then he asked a question which became relevant later on. So is that true? Is that still true if A is not an abelian variety but abeloid? An abeloid, which means a proper rigid analytic group. group variety. So rigid analytic version of abelian varieties. So he asked that, and we didn't know how to answer this question until around 10 years ago or so, 12 years ago. The answer is yes now. But for that, we had to develop a very much more powerful theory of p-adic geometry than we used before. So
what's the index of H0, A omega 1?
-1.
No, the index.
It's tensor with C, sorry, because
Oh, it's a C.
The Hodge group is over case. So then it took some years, and then became the work. So we just knew that it's true for abelian varieties. Then the first breakthrough came in the work of Fontaine-Messick, and that's around 87 maybe, 85. And in their case,
could you give a prototypical example for the proper rigid analytic groups for people who have no clue?
So can you say what an abelian is? Not the definition, but like an abelian variety has only a finite number of parameters. It's something very concrete. Okay. And this, I mean, since I don't know these things, are they classified, these abelians?
That I don't know. I don't know.
So are there examples?
No, there are examples. They arise, for example, I think from the moduli spaces of, I forget which structures, but there are some concrete examples, but they are, esoteric.
It's not an explicit object, like abelian varieties are very explicit. Over C, you can write.
There's the group, the torque, some category.
No, that's what I'm asking. Is there something concrete like Torah, abelian varieties, or is it just?
Right.
I mean, I don't know about rigid things. Are there a huge number of these? Are they classifiable?
Yeah, I'm sorry, I didn't really follow much on abelians.
No, but why does one ask this question if one doesn't? I mean, presumably one's interested in these abelians. That's the question.
Well, no, I mean, the question, no.
Yeah.
The question of Tate was more about, he was more interested in rigid analytic varieties in general. Okay, because they arise everywhere if you try to do p-adic geometry. And this was something with abelian varieties was something he could access. And then the question was, is it also true if the abelian variety is non-algebraic? And apparently,
Okay.
about examples.
But the actual
that was like the simplest case. But in fact, the proofs we have now, they don't go that way. I mean, we don't do the simplest case, and we actually have a proof for all proper rigid analytic varieties. We don't distinguish abelians. Abelians arise, though, in recently quite a lot in a different strand of p-adic geometry, which is the Simpson correspondence. There they study them carefully, but I didn't look at that. And so rigid. So it's kind of curious because when we try to prove this kind of theorems for algebraic varieties, you in fact naturally do everything in the rigid analytic setup. And then you are blocked because you don't have tools, so you have to algebraize things, etc. So it becomes very difficult in the story. But these days you actually don't have to do this. This is what I was trying to explain, that you can really work in the rigid analytic setup instead of working with formal schemes and the algebraic versions. So for Fontaine-Messick, so they tried to prove this conjecture and its generalizations, which I will explain. So they had to assume projective varieties. We also have to assume that P is large. So this is a standard assumption which comes in the theory, which has to do with torsion. It's in general. So P, for example, if p is larger than the dimension of x, then computations become much simpler. And so they prove it in that setup, and they use what we call now symptomic methods. So what are those? Well, you are looking at the cohomology. So if you have some models, then you can pass from this cohomology to p-adic nearby cycles. And then this p-adic nearby cycles, the symptomic method expresses as some complex of differential forms. And these kind of ideas go back to the work of Bloch, Kata, I don't know, 83 or something like that. Okay. But so that was big progress, but then came the work of Foltings around 87, and he tried to do two things. So first, prove this conjecture in general, but also do so plus do coefficients. So what do we mean by coefficients? That is, if I have a map between two algebraic varieties, I would like to actually study cohomology of push forwards of TP, for example, and study cohomology of this type of shifts, and have similar theorems. And so what he was able to do plus x was now for him proper. No restriction on p, but the technique he used was different. So this is what we call now almost italic extensions. So this goes back now to Tate's approach. So generalization of Tate's approach. So what's the idea here? The idea is very nice. So the idea is, which we use all the time now, in what we call perfectory geometry. So we don't have a resolution of singularities in mixed characteristic, right, or characteristic P. So we replace it with this kind of techniques now. That is, Tate observed but in dimension 0, but Foltings then extended to any dimension, and then with the approach of Scholz, so this became much more powerful. That we can use towers of highly ramified extensions by attaching p roots of coordinates to actually mimic existence of smooth or semi-stable models. So to resolve singularities. So I can't quantify it because it's difficult to actually, there is no particular theorem which does it or anything. But in practice, that's what we are observing. That is that we can replace non-existent resolution of singularities by this kind of perfectoid techniques. And people who do geometry mod P these days, or mixed characteristic geometry, not arithmetic like I do, but really geometry, then they use it with great success now. This approach. Okay. So this was apropos Tate. So one thing I want to mention, what follows from this Hodge state comparison theorem, is that the generation of the Hodge, the Rham spectral sequence. So we have have the Hodge-Rham spectral sequence, and it degenerates at the first page. So this could be proven from this conjecture just by counting the dimensions, right? If you count the dimensions, you get that it has to degenerate. But there's also a proof. I don't remember. It's around the same time by Bellini-Lusi, which uses spreading out reduction to characteristic. Okay, so these are the facts concerning the Hodge filtration. Now, the second part is that for arithmetic applications, we need more. So these are the fine structures. On cohomology. So under our cohomology. So for that, we use reduction. So this comes from reduction mod P. And for reduction mod P, obviously we have a Frobenius. But also we are going to acquire monodromy. And I will try to explain how we get monodromy. So let's look at the simplest example. That is, I'm assuming that my variety over K is actually a generic fiber of a scheme. So this would be over spec of K. Scheme over OK, which is semi-stable. By semi-stable, I mean the divisor. Let's just take, so this is proper, that there is a divisor, the special fiber is a divisor with normal crossings with no multiplicities. So we have special fiber. So this is over spec. Okay, and here we have spec of K. And this is normal crossings divisor. Okay, and now we have what we call Rham, or Rham I, which is the Rham cohomology of the generic fiber. But we also have something more refined, which is what we call Hiodo-Kato cohomology, which is attached to this model, integral model. And what is that? So that is defined as using the special fiber. So this is crystalline cohomology of the special fibers with respect to V vectors. And there is some funny object here. So let me explain this. So this is crystalline cohomology, so it's some good variant of the Rham cohomology with characteristic P, of course. But now it's a special fiber, so you naturally have a Frobenius action here, by factoriality. Now this object here, it's a degeneration of the affine line over the V vectors. So it has this kind of tangent vector here. That's what this zero means. You have a sticking tangent vector, which means that kind of allows you to define monodromy action. And there is some relationship between the monodromy and Frobenius. And now,
can you say what this vector is once again? It's zero.
It's a log structure. So you basically take affine line over W, so WT, and then you send T to 0. So you have d log T, and then if you send T to 0, this is like attaching d log 0.
Where does this T come from? In your setup, there was no family, right? No T. And now there it is.
Right, no. So I am just trying to explain how you can think about this and the fact that there arises monodromy. But what I mean is that you are just formally attaching d log 0. That's what we mean formally. But actually, in computations, you often do deform to the whole line. You just try to do computations. At least when you try to see monodromy on the level of complexes, you often write it as a boundary map, and the object in the middle, which appears, is actually this guy over WK of T. that allows you to see monodromy as the boundary map. But in the definition, you don't have it.
Yeah, then you take cup products of d log 0 with itself, or if you have cohomology operation, or when you say you add this to your structure, is that there are rules how to then deal with it?
Yeah, so this is all encompassing this theory of log schemes. So what you keep in track of here is not that, I should say that you don't think about this, I didn't say this should be formally like a log crystalline cohomology. So this is not just a scheme, it's a scheme plus the log structures which come from all these coordinates at a special, defining, you remember those. And you remember that in the base is d log 0, which you want to, if you take differentials, you want to manipulate d log 0, so this introduces certain relations. Okay? But the main thing I wanted, it's not so important in fact. So for example, imagine that this guy has good reduction. If that guy has good reduction, then you can just forget that. There is no monodromy. Okay, so this monodromy just keeps track of the essentially semi-stable reduction. And the reason I am mentioning it at all in such detail is because that's the way I see monodromy, right? Monodromy comes from the existence of this structure. And again, if you want to write it really explicitly as a boundary map, the monodromy, then you write this group here on the level of complexes. Then you have something here over the line. And then again this group here. Something like maybe there should be a shift here or something. And so in that sense, this guy arises in the definition of monodromy, formally speaking. But conceptually, you just have something which allows you to go around.
Do you require your semi-stable models to always be regular?
These ones are regular.
Always.
Sorry, I can say. They are regular and no multiplicities, I'm assuming. But in general, you don't have to do that. I will mention it in a moment. But here, I just wanted to be simple. In fact, in general, this works quite well if this is what is called log smooth. So, log smooth. So in particular, you can assume, you can, for example, take a product of two semi-stable, and you are still in this setup, which is what is called formalism of log schemes allows you to do, which is very nice. So this group maybe looks a bit funny, but actually it's not so mysterious in one sense. That is that we have a Chodokata isomorphism. So this was all developed by Chodokata in a series of few papers between this crystalline cohomology. So this Chodokata cohomology, and so this one. I should say this one is, what is the field of definition here? I am over a bit vector, so this is the absolutely unramified subfield of K. That's the field of definition. And if you change to K, you just get the Rham cohomology. So in that sense, this is a structure on this. And in fact, it's kind of, here it looks like it depends on a lot of choices, but in fact it doesn't. Okay, so you have this. In particular, this means this is a final drunk over K naught. And it has this Frobenius and monodromy. And this isomorphism. What else do I know about this? The one remark I want to make, which is very important kind of philosophically in applications, is that if you take these structures here, in general, there is one more thing coming here. Then this behaves like a Tal cohomology, but with QL coefficients different than P. So I put it in the quotation marks here, but this can be made quite precise. So there is also some residual action in general of Galois group. And so you can represent, so if in which sense these are similar, It is in the sense that you can think of this as a representation of the Veil-Delin group. Okay? And this, of course, you can also think about by Grothendieck as a representation of the Veil-Delin group. Sorry, this should be algebraic and one. And now we can make it precise. We want these two representations to be the same. So in that sense, the two guys should be the same. So that's like a guiding light for how these things behave.
So can I just ask a quick question? Could you elaborate on what you meant by the isomorphism of Hirokato does not depend on all the choices that it seems to depend on? So you have to choose a uniformizer. But
Oh, no, sorry, yeah, but these days we just choose P. Yeah, so if, we just, assuming that you made that choice.
right, yes.
Because these days we really, I will explain in a moment, but we really have to vary this thing with the field, and then the choice, so it's a good question, but a priori the original definition depended on the choice of the uniformizer, but we choose the P as the, because that doesn't have to be uniformizer. So we choose P as the canonical guy, and then you can vary it with K. So now I have to erase the board, so if you have any questions.
Maybe a quick reminder on the Veil-Delin group. How can we think about?
So it has action of inertia, and it has this monodromy operator. So well, basically, forget the group maybe. So basically, what it says is that if you look at the action of Frobenius and monodromy on both sides, analytic and p-adic, we are going to match. So for example, if n is 0 on one side, it should be 0 on the other side. Okay? You can, so we know that the structures, for example, also live on realizations of the fundamental groups, the important ones. And there, I think the question is still open. The L equal P question, well, in general for matrix is open, but in particular for the realizations of the unipotent fundamental group, I think I don't know, do you maybe remember? Do you know maybe? No? Someone knows? Yeah. What's the status? But I think it's open whether it's true for the fundamental group. The L equal P. So if n is 0 on a analytic side, is it also 0 on the p-adic side?
I think something far more naive. So it's a group that's acting on the filtration or coming from the absolute gamma group of.
Yes, yeah. So you just think about it as a representation of the Galois group, but you are trying to kill topology. Because then you can compare L and P. So you are replacing it with the Veil group, and then the Delin just keeps track of the monodromy.
It's still this huge group acting.
Or it's GA cross Veil group.
Okay.
But you can now make sense out of this equality for L equal P. Okay, so we know that we have these structures there. So that took some time to work out, but then Fontaine and Janssen. So there were two parallel stories here happening. One was that we knew that we are coming up with these structures coming from geometry, but another story was, well, what if we abstract these structures and study them as, abstract categories. What kind of restrictions we can put on them, or what kind of interplay we are seeing here. And so that was another thread. This is the work of Fontaine and Janssen. We look at this abstract triples now. This DST, which is like the Hodge object over there, the Rham object, and then this comparison between these two. So this Hodge object. So they abstracted, I won't write it, but they basically abstracted this data into this kind of triples and call them, so let's call them filters. 5 modules. And then there were two notions to narrow the category to the ones which come from geometry. So one was weakly admissible. So the question here, maybe let's put the question here. So how can we describe this coming from geometry?
Is this the p-adic analog or a p-adic analog of the Rham-Betty plus the isomorphism between them, or that's?
No, it's a p-adic analog of limit Hodge structures. So these are limiting Hodge structures. That's the way you should think of it. The p-adic analog of what you just said is the comparator values. Okay. And this is like a limiting. So this Hodge is like a limiting Hodge structure on this general guy.
And the limiting is with this D-longs, or when you say limiting, I don't see any limit.
No, the limit is that you have family over OK. That's the family, right? So this is for us like a disk. And you have generic fiber, which is xk, and you have a special fiber, which is x naught. Okay. So how can we describe this kind of triples which come from geometry? So what restrictions we can put? So so there were two. One was combinatorial. So this is a combinatorial. So this description is very simple to state, not so easy to understand. So weakly admissible. Now we don't say this, and I'll explain why. If the following holds, so let me just explain. So I look at two objects. So one is the slope of the Frobenius. So this is slope of the Frobenius. The other is the slope of the Hodge filtration. So just think that everything is one-dimensional and then these definitions make perfect sense. So this is slope. So there is a slope of Frobenius and Newton slope and Hodge slope. And second, and this condition means that if you write Hodge polygons and Newton polygons, then they are going to have the same endpoints. And for every d prime in D, so substructure, d and d prime, which way it goes, is above dh d prime. So Newton polygon lies above Hodge polygon. So these are type of restrictions that we've seen in p-adic geometry since the 60s at least, right? So they are formalized here, including also the monodromy somehow.
What is the phi determinant of?
If this is one-dimensional, this is just slope of Frobenius.
Phi is Frobenius.
Yeah. Phi is the Frobenius. Okay, so this is the one definition. And the other restriction was the following.
Excuse me, I could what does it mean? D prime. D prime is
Sub-object of D in all this with all these structures.
Sub-object.
Preserving all these structures. So if this is called admissible, if the following holds. So this is a bit more mysterious definition, and that comes from the Betty-Rham type of comparison, so period isomorphism. So you define a functor which is called dst of z in the following way. You take this dst, you transfer it with the period ring dst, you take phi equal a 1 and equal 0. I will explain in a moment. And then you take filtration, p-adic and p-adic. Okay, so I'm sorry that at this point it kind of comes out of nowhere, but the idea is that this functor which you see here, so these are period rings. So contain period rings. So this one is actually a field. If you like, it's a C. We've attached one parameter, which is, so you attach contains T, which is like 2 pi I. Plays the role in p-adic arithmetic of 2 pi I. And VST is a period ring which also has a Frobenius and monodromy. So it's supposed to, it's a subring of this. So morally speaking, these are, so we know that if you look at periods of algebraic varieties, p-adic algebraic varieties, C is not enough, C is too small. So you look at this p-adic. It turns out that p-adic is actually completion of C or completion of K bar with respect to a topology which is unusual. So that was proved by Colmez at some point. So if you complete C K bar with respect to a different topology, you get all algebraic periods, p-adic periods. Okay, but you get too much. So this one is inside p-adic and it has less periods. Okay, so you want this, and it's supposed to be a better approximation to p-adic period ring than p-adic. It's too large. Okay, and so that was one guess for what would be the ethyl cohomology as a functor from the Rham cohomology. So this is Galois representation. So everything here has Galois actions, a Galois representation, but it can be infinite dimensional, and you will see. So, but these are admissible if the dimension over T of this functor is the same as the dimension of p-adic. The dimensions are equal, then this is called admissible. So you see that it's very indirect definition. And now Colmez and Fontaine proves around, I don't know, 99 maybe, that these two definitions are these two categories are the same. So that is, we knew that it's not difficult to show that if it's admissible, then it's weakly admissible, but to show that if it's weakly admissible, then actually this dimension is what you would expect was difficult. So now we can distinguish between these two categories. And now in Tsuji, around 98, he has shown that if you take X in that setup over there, X, you take X and you associate to it this B, I, then this is admissible. And you would think that the proof would go like that. Well, you have all these the Rham cohomology there. You have this combinatorial data, you just show that these properties are satisfied, right? But in fact, no, that's not the way proof goes at all. So it's difficult to show this. So in fact, what he does, he first proves comparison theorem. So he proves that VSP of D is actually isomorphic to a type of homology of Wieslawa action. And from that, he induces, now we know that.
How do you have an I on the right, but not on the left?
Okay, and looking at the remark that
You have dimensions really over two different fields, QP and K, or is that?
yes, this one is a QP vector space because the coefficients here we took were QP. This is K because our variety is over K, so the Rham differentials are over K. Okay, so this is semi-stable model. So for application, semi-stable models are where we need more general theory. So now there exists a general theory when X is anything over K. So any variety. If X is any variety, so what happens then? You still get these pairs. You have DSP. You can define what you mean by Hodge, and you have the Rham objects, and you have this comparison, but you have a little bit more. You have residual Galois action, so factors for a finite quotient. That's what I mean by residual. And that refers to this. So there is an extra structure on this ESP. So why is that? And then you can prove exactly the same things. So why is that? It's because here we are assuming semi-stable reduction. We don't have geometric potential semi-stable reduction theorem in the mixed characteristic, but we can kind of mimic it, right? The cohomology seems to behave as if we had it. So using alterations locally for H topology, you can actually find semi-stable models. There you define your Hodge cohomology and then you glue. But because it's potentially semi-stable, right? So you have to extend the field. Then this Galois group remembers this action here, remembers that you have to go up. So there is a little bit more of data. And now when we work with this kind of structures, this is the package we work with. Okay? Remembers all of this.
Sorry, when you say variety, it's still an algebraic variety, it's not originality.
But I just finished algebraic varieties. So that's basically most of the story. I didn't say anything about the coefficients because I want to pass to the analytic story, which we don't understand very well. The algebraic story we understood pretty well. Although the theory of coefficients is really good, coefficients is still really missing. So now I want to pass to the analytic story. And in the analytic story, if we assume rigid analytic varieties are proper, then the p-adic Hodge theory, which I sketched, behaves very similarly. The situation is that we are not that interested in proper rigid analytic varieties, right? The varieties we are interested in are like the inverse space, so p-adic symmetric spaces. And so the proper rigid analytic varieties are just like a proper example to us. So that's something that maybe you should keep in mind, that why we are interested in rigid analytic varieties. So analytic varieties. motivation comes from p-adic symmetric spaces. And so I will give some concrete examples. And one way you can define p-adic symmetric spaces, and that's what that Rappaport and Orlik-Rappaport book talks about, is actually using these structures. I will try to mention how these structures allow you to define good class of p-adic period domains, actually, or analogs of those. Okay, so rigid analytic varieties. So let's look at the first case in which we are proper and smooth. And here the slogan is that p-adic Hodge theory, so what I sketched, is very similar. Although it took us a long time to prove that, because we were just technically too weak for a long time. So what are the examples here? So we have, of course, analytification of proper algebraic, smooth algebraic varieties. Then it's the analog of a Hopf surface as well, for example. The Lois, which I mentioned. Yeah, so not that many examples for proper case. But it was something that we started with, because we at least can control functional analysis in this case, which was already something. So let's look at the first theorems. So this was Scholze around 2011. So he has shown that, in fact, in this case, so this was not known, but if you look at the cohomology, with ZP coefficients, this is finitely generated ZP module. And I think his proof, which uses kind of a very Artin-Schreier, so by Artin-Schreier, kind of p-adic Artin-Schreier, if you will, actually Artin-Schreier. It reduces to some coherent statement, which then can be proved by techniques similar to those coming from analytic coherent sheaves in complex analytic setup. And I don't think we have a different proof of this statement for the moment. And it also is zero if I is larger than 2 times the dimension. So it behaves rhizometry. Then he proved also this Hodge state comparison theorem. So we have a Hodge state decomposition. And here you see difference. That is, if your variety doesn't come, I assume it comes from discrete valuationing, but if your variety doesn't come from discrete valuationing, but is really genuinely defined over C, then you don't have Hodge state decomposition, you have a Hodge state spectral sequence, which doesn't degenerate. So there are differences showing up, and then this gives you the generation of the Hodge spectral sequence. So this looks very similar to the story to the algebraic story. So let me mention just a remark. So this is where Scholze introduced the most powerful techniques of this perfect story geometry these days. So he uses almost a third theory. And again, what he proved is what something Frobenius tried to prove, which is almost purity result. So Frobenius didn't have that proof. So he had only partial results, but in fact, surprisingly simple, the modern proof of the theorem, and it's very powerful. It allows you to work on the generic fiber, in character over QP or on the analytic varieties. You don't have to constantly look at the models, which is a big thing. Okay, what about the finer structures? Because that's just the Hodge filtration story. So again, you can basically do similar constructions. So you can associate these couples to the cutoff, the Rham with the filtration, and this residual Galois action. So how do you define the cutoff? Well, I am assuming X is smooth here, so that means that I can actually use the eta local alteration of Hartley and Temkin, and they tell you that eta locally on X you can actually find semi-stable models. So if you have semi-stable models, you can again define this monodromy and Frobenius, etc. So you again have all these structures here. And here you have the residual Galois action. So all of this looks very similar, modulo the path of getting there to the algebraic setup. Now we prove the theorem. So that's my young work with corners 16 and 25. That you look at this couple. This is again admissible. And if you look at the associated representation to this, then this is the same as the eta cohomology of the variety of QP coefficients. Okay? So I wanted to tell you more about the non-proper case, but I ran out of time, sorry. Let me just mention two things. One is that, so there is an application of this. There is a question which we studied in the algebraic setup at some point. You look at the Grothendieck group of vector bundles on K, and you look at the elements which are homologically equivalent to 0 in the sense of this homologically means these groups here. Then you get a factorization, what you say, spectral sequence. Of this type, coming from strand classes. And now we know these guys are potentially semi-stable in the classical sense. Here, this theory. So you can ask whether this lands here in the classes which are geometric. Again, this is finite rank, so you can ask this question. So are these strand classes geometric? Here are strand classes. And in fact, the answer is yes. So we have this factorization through geometry. So what is this H1G? So in the usual Galois group studies extensions of QP by this in the Galois representations. The G is studying the same extensions in the admissible data. So we are saying that all these chain classes here are actually coming from geometry. So